In this online lecture, we derived some of the formulas for numerical integration. When we speak of numerical integration, we take a function f of x equals y and find the value of the definite integral of f on the interval from a to b. To be more precise, when we say numerical integration, we estimate the definite integral. Examples of numerical integration include Riemann sums. Two of the more familiar examples of Riemann sums are the left sum and the right sum. When using Riemann sums, we partition the interval from a to b into subintervals using nodes or partition points x sub 0 through x sub n. While typically for a Riemann sum, the length of the subintervals need not be uniform, we will use a uniform partition here. That is, delta x or h is equal to the length of the anti-interval b minus a divided by the total number of subintervals. For the left sum estimate, we take the y value at the left endpoint of each subinterval and multiply it by h. In the case of a continuous and non-negative function, as what is shown on the screen, the y value at the left endpoint multiplied by h represents the area of a rectangle. So for the first subinterval, the product f of x sub 0 times h represents the area of the rectangle, estimating the area between the graph of f and the x-axis on the first subinterval. This is true for every subinterval. On the other hand, the right sum estimate uses the y values at the right endpoints. A third type of Riemann sum is called the midpoint rule. As the name suggests, this uses the y value at the midpoint of each subinterval. So for example, on the first subinterval, halfway between x sub 0 and x sub 1 is m sub 1. Find the y value there. Use this y value to form the rectangle, and then the area of the rectangle estimates the area underneath the graph of f. We replicate this idea for the other subintervals. So if we take just the first three rectangles, the sum of the areas of the three rectangles will be f of m sub 1 times h for the first rectangle, plus f of m sub 2 times h for the second, and f of m sub 3 times h for the third. Factoring out h, we get this expression, and generalizing to n rectangles, the integral from a to b of f of x is then approximately equal to h times the sum of f of m sub I, where I goes from 1 through n. We take a look at three other techniques, all of which are based on interpolating polynomials, or what we call the Lagrange polynomial passing through the given points. The first technique is the Trapezoidal rule. For the first subinterval, we take the leftmost and the rightmost points on the curve, connect these two using a straight line segment, and this forms the top of our trapezoid. The area of the trapezoid then estimates the area underneath the curve. Then replicate the process for the other subintervals. We can use the geometric formula for finding the area of each trapezoid, but what we will do here is to use the Lagrange polynomial to figure out the area of each trapezoid. To find the area of the first trapezoid, we find the equation of the line forming the top of the trapezoid. That should be an easy exercise since what we are looking for is just the equation of a line. But we will not use standard equations of lines to find this equation. What we will use is what we might call the Lagrange form for the equation of a line. Using a computer software, we define x sub 1 in terms of x sub 0. X sub 1 is equal to x sub 0 plus h. We then define the function, which we call Lagrange of x. We take the y-coordinate at the first point, y sub 0. And then we multiply this by a fraction. The numerator is x minus x sub 1, not x sub 0. The denominator is x sub 0 minus x sub 1. Then we use the second point. We take the y-coordinate y sub 1, multiply this by a fraction. The numerator is x minus x sub 0 this time, and the denominator is x sub 1 minus x sub 0. This is another form for the equation of the line through the 2 points at x sub 0 and x sub 1. We just have to integrate it from x sub 0 to x sub 1. We type in our function, integrate with respect to x. We'll also ask the machine to factor out the result. Evaluating these lines of command, we get this result. In this result, y sub 0 and y sub 1 correspond to the 2 vertical heights of the first trapezoid. Of course, y sub 0 and y sub 1 are f of x sub 0 and f of x sub 1 respectively, so that we can write down the formula for the area of the first trapezoid as half of the sum of f of x sub 0 and f of x sub 1 times h. Extending this idea to the second and third trapezoids, we get similar formulas so that we get the total area for the 3 trapezoids. And the composite formula for n subintervals, and also the estimate for the integral from a to b of f of x, is given by this formula. For the next numerical integration technique, we will still use the Lagrange polynomial, but instead of taking 1 interval at a time, we will take 2 intervals at a time, or 3 points at a time. The method is called Simpson's 1/3 rule, and this is how it goes. First, we define x sub 1 in terms of x sub 0. X sub 1 is equal to x sub 0 plus h. And do the same for x sub 2. X sub 2 is x sub 0 plus 2h. Then we construct the Lagrange polynomial through the points at x sub 0, x sub 1, and x sub 2. Calling our polynomial Lagrange x, it starts out with y sub 0 from the first point, times a fraction. And the numerator of this fraction is the quantity x minus x sub 1 times x minus x sub 2. The denominator is x sub 0 minus x sub 1 times x sub 0 minus x sub 2. For the next term, we have y sub 1 from the second point, multiplied by a fraction whose numerator is x minus x sub 0 times x minus x sub 2. The denominator is x sub 1 minus x sub 0 times x sub 1 minus x sub 2. From the third point at x sub 2, we have y sub 2 times the fraction whose numerator is x minus x sub 0 times x minus x sub 1, and the denominator is x sub 2 minus x sub 0 times x sub 2 minus x sub 1. The graph of this function is either a line or a parabola passing through the 3 points. If the graph of this Lagrange polynomial does not dip below the x-axis from x equals x0 to x equals x2, then the integral of this Lagrange polynomial represents the area between the graph of the parabola and the x-axis. Regardless, the integral from x0 to x2 of Lagrange x represents an approximation for the integral from x0 to x2 of f of x. This is what we get when we carry out the integration and have the result factored. You can see why it's called Simpson's 1/3 rule. The formula that we have on screen is taken for the first two subintervals. We get a similar formula for the next two subintervals, and the next two, and the next two, and so on, so that if we combine the results, we should get this composite form for the estimate for the integral from a to b of f of x. Keep in mind that the number of subintervals should be even. The last numerical integration technique that we present here is called Simpson's 3/8 rule. Instead of using just 3 points or 2 subintervals, as we did for Simpson's 1/3, Simpson's 3/8 rule uses 4 points or 3 intervals at a time. Because for Simpson's 3/8 rule, we are using 4 points at a time, the degree of the Lagrange polynomial will be of utmost 3. If the graph of the Lagrange polynomial does not dip below the x-axis from x0 to x3, integrating the Lagrange polynomial, we get the area between the Lagrange polynomial and the x-axis. This expression represents precisely that area. We can find this using a similar process that we used for Simpson's 1/3 rule. Replicating the process for the other subintervals, remembering to take 3 intervals at a time, we get this composite formula for the estimate for the integral for f from a to b.